last time we defined this cofactor of a tensor. So cofactor T ij is equal to half of epsilon I m n epsilon j p q t m p t n q. And I also wrote some of the elements of this cofactor T. So this cofactor T matrix looks something like this. So this is T22, T33 minus T23, T32, and so on. Okay, so I will not write all the elements. Last time I think I wrote most of the elements, and also it is given in the book or in the notes, in the maths notes. Okay, so you can take a look at that. Now, if you take the trace of this, so then you will get that trace of T, trace of cofactor T, trace of cofactor T, that is equal to cofactor T I. Okay. So wherever J occurs, you put I, and then you can use the epsilon delta identity to simplify this. So you will get that this is equal to half of trace of T square minus trace of T square. Okay, and if you recall, this is exactly the second principal invariant. Right? So this is we had introduced the three principal invariants. So I1 was equal to the trace of T. I2 is equal to the trace of the cofactor, or it can also be written as half of trace of T square minus trace of T square. And I3 was the determinant of T. So these are the three principal invariants of T. So the new result here is that I2 is also the trace of the cofactor of T. Fine. Then now if I multiply T with cofactor T transpose, then let us see what I get. So T times cofactor of T transpose times Ij. So this is equal to T Ik times cofactor T Jk. Now I will just simplify this expression using the expression for the cofactor. Simplify this particular expression. So if I now write the components for cofactor T of Jk, then I will get the following. So this is equal to half of epsilon of mnj, then epsilon pqk, then tmp, tnq, tik. So I have simply substituted for the components of the cofactor into this particular expression here. Okay, then we will use the expression for the determinant of T, which I had introduced earlier. So here I can write this as half of epsilon mnj times epsilon mni times determinant of T. So this is one of the expressions. So this part here is equal to this whatever is written in the bracket. So this I had introduced when I was discussing the expression for the determinant. At that time I had introduced this particular relation. So I am just using that particular relation. So this is equal to nothing but, so now you can see that this epsilon mnj times epsilon mni is 2 times delta ij. So this is equal to determinant of T times delta ij. So that is just, I am using the relation between the alternate tensor and the canonical delta to get this. So similarly, we can also show that so now I am writing it as cofactor T transpose times T. So that if you write, then that is equal to determinant of T times the identity. Okay, so this delta algebra means these are the components of the identity tensor. So here you will get that cofactor T transpose T is the same object, that is determinant T times the identity tensor. So in general, see I have mentioned this before. In general, okay, in general, RS is not equal to SR, correct? But in this particular case, it turns out, in this case, it turns out that T times cofactor T transpose is equal to cofactor T transpose times T is equal to determinant of T times the identity. So this is the relation that they have shown now. So in this particular case, they compute. Okay, so this is then it doesn't follow this general rule in this case. Okay, now we'll use this cofactor T to define the inverse of a second order tensor. So uh, okay, so now we have seen that we define PT inverse to be identity. Right? So if I take the determinant, so assuming that T inverse exists, then if you take the determinant on both sides, then you'll get that determinant of T times determinant of T inverse is equal to 1. So from this, you can see that this implies that determinant of T is not equal to 0. Because, see, suppose if determinant T is 0, then this equality will get violated. So that means, because this product is equal to 1, we get that determinant T is not equal to 0. So what I am trying to show is that T inverse exists if and only if determinant of T is not equal to 0. So here I have shown that if T inverse exists, then determinant T is not equal to 0. Now conversely, I will also show that if determinant T is not equal to 0, then T inverse exists. Okay, so that is the converse now. So conversely, if determinant, if determinant of T is not equal to 0, then then we will use this particular equation. So what I will do is that I will just simply divide this equation by determinant of T. Okay, so if I divide this, then what do I get? I will get, so suppose determinant T is not equal to 0, right? Then T times cofactor T transpose divided by determinant of T is equal to cofactor T transpose divided by determinant of T times T is equal to identity. So this implies that T inverse is equal to cofactor T transpose divided by determinant of T. So what we have shown is that if determinant T is not equal to 0, then this inverse exists, right? And if T inverse exists, then determinant T is not equal to 0. So in fact, we have not just shown that T inverse exists, but we have also given an explicit expression for T inverse, right? In terms of this cofactor T for matrix. So this is just substitute the expression for cofactor T, that matrix expression which I wrote at the beginning of the class. Just substitute that, divide it by the determinant of T, and then you will get an explicit expression for the inverse of T. So using now some of these formulae that we have derived, we can write some properties now of T inverse. So let us note down a few properties of T inverse. So So now we have that T inverse is equal to T inverse T is equal to I. So, so actually, so we don't need to define a right inverse and a left inverse because of this particular relation. So, whether you multiply it from this side or from this side, you will get that the same result. Okay, so otherwise, suppose if these two objects had been different, then we would need to define left inverse and a right inverse. But fortunately, that doesn't happen because T inverse turns out to be T inverse T. Okay, so that's one nice result that follows from this cofactor relation that I have written. Then now using the cofactor T transpose is equal to cofactor of T transpose and cofactor of Rs is equal to cofactor R times cofactor S. Okay, so these two properties you can try to show using initial notation. Okay, so that I had already written down the explicit expression for cofactor in terms of the alternate tensor. Use that definition to show these properties. So cofactor T, the whole transpose, is cofactor of T transpose, and cofactor Rs is cofactor R cofactor S. Here again you have to be very careful. This cofactor of R is a second order tensor, and cofactor S is also a second order tensor. So you cannot interchange it. Okay, you cannot interchange the order in which you write this. So for example, you cannot write this as cofactor S times cofactor R because so I mean in the case of determinants you can do that because there it's a scalar. So determinant of Rs you can write as equal to determinant R times determinant of S, correct? And you can also write this as equal to determinant of S times determinant of R, correct? So here the interchanging is allowed because we are talking because these are scalars, but here these are second order tensors. So as I said, you have to be careful that you should not interchange the order of this cofactor. Fine. Now using these relations, you can show that T inverse transpose is which is defined as T inverse transpose. So that is equal to T transpose inverse. So basically, as I said, use this particular relation to show that T inverse transpose is equal to T transpose inverse. So because T inverse transpose turns out to be T transpose inverse, I can also write it as T of minus T. See, suppose if these two objects had been different, okay, then such a symbol would have been ambiguous because then I do not know whether this T minus T that I am writing refers to T inverse transpose or whether it is referring to T transpose inverse. But fortunately, again, both these objects turn out to be the same, and hence you can define this T minus T as either of them because they turn out to be the same. Okay, so try to show this particular relation using this relation here. That cofactor T transpose is cofactor of T transpose. And then you also have Rs inverse is equal to S inverse R inverse. Okay, so one property that I have not mentioned so far is that the inverse is unique. Okay, so inverse is unique. So inverse is unique. So if you find one inverse, then you are done because you don't need because you know that I don't need to look for any other inverse because of the uniqueness. So that is a very nice property because, for example, suppose if this is the claim, right, and if I show that S inverse R inverse is one inverse of Rs, then I don't need to look for any other inverse, right? So directly I can write that Rs inverse is equal to S inverse R inverse. So here let us try to show this. So here, suppose if I write S inverse R inverse times R times S, correct? So this should turn out to be identity. So this is S inverse times identity times S, which is equal to S inverse times S, which is equal to identity. So as I said, you can see that S inverse R inverse is one inverse, right? And so because of the uniqueness of the inverse, it is the only inverse. Okay, so so you can use this uniqueness. So suppose you manage to guess. I'm not recommending that you should always guess. So there are more systematic ways of finding out the inverse. But suppose in a simple case like this, you did some guesswork and you found out an inverse, then just by the uniqueness of the inverse, you don't have to look any further. So this acts as the inverse. And then Tu is equal to V is equivalent to U is equal to T inverse. So this is, so basically if you just multiply both sides by T inverse, then you will get this particular relation. And again, if you multiply this by T, then you will get back this particular relation. So these two statements are equivalent. Of course, here in all these cases, we are assuming that the inverse exists, and that we have given the necessary and sufficient condition for the inverse to exist, which is that determinant of T should not be equal to 0. Okay. So now we'll start considering special cases of tensors. Okay, by special we mean tensors such as skew symmetric or symmetric or orthogonal. Okay, which have some special properties. So we will start with skew symmetric tensors, and then we will go to orthogonal tensors and see some of the properties of that and so on. Fine. So first we will start with skew symmetric tensors. Yes. So so this is SKW. So so typical elements of this set of skew symmetric tensors I will denote by W. Okay, so this is just a typical notation for skew symmetric tensors that is used in the literature. So I will use that. Basically we have that W transpose is equal to minus W, right? By definition of a skew symmetric tensor. So now actually if you write out, suppose if you write out the components of W in a given coordinate system, right? Then what you will get is that you will get, so this will be 0, right? Then you will get W12, then you will get W13, then you'll get minus of W12, then 0, then 0, then this is W23, this will be minus W23, and this will be minus of W13, right? So if you take the transpose of this, then you'll get minus of that, right? So that you can easily see. So you can see, and the diagonal elements have to be 0 because transpose has to be equal to minus W, the diagonal elements have to be 0. So here you can see that there are only 3 independent components, right? So any skew symmetric tensor in any written in any basis will have only 3 independent components, and a vector also has 3 independent components. So we can relate a skew symmetric tensor to a vector, okay, because of this particular fact here. So let us see in what sense we can identify a skew symmetric tensor with a vector. Okay, so let us see that. So theorem given W belonging to skew, there exists. So this symbol stands for there exists a unique vector, a unique vector W belonging to V, known as the axial vector. Corresponding to W, such that WU is equal to W cross U for all U belonging to V. So here do not confuse between the capital W and the small w. Okay, the capital W stands for the skew symmetric tensor, and the small w is a vector. So here this is the small w. So capital W and u is equal to this small w, which is the axial vector cross u, and u can be arbitrary. Okay. So here in this particular case, this defines the axial vector of a skew symmetric tensor. So what we are saying is that if you give any skew symmetric tensor, we can find an axial vector such that this relation is satisfied. Okay, and conversely, if you give me a vector small w, then there exists a skew symmetric tensor such that this relation holds. So that also I write here. So let me call this relation as star. So conversely, given any vector w, conversely given small w, right, belonging to V, there exists a unique capital W belonging to skew such that star holds. Yes. So this uniqueness is important. Okay? So there is a unique and this also. So if you give me capital W, I can find a small w, which is the axial vector, such that this star relation holds, and this small w is unique. Conversely, if you give me a vector small w, then there exists a skew symmetric tensor capital W such that again star holds, and then this capital W is unique in that particular case. So this is a theorem. So I am not going to give you the entire proof. The proof is a slightly complicated. So as I said, that since this is a beginning level class, I will not give the entire proof for this. So I will just present the initial notation version of this particular relation. Okay, and I will also tell you how to construct small w if you are given capital W, and to construct capital W if you are given small w. So if you are interested in the detailed proof, take a look at the book, my book, that first volume. There the detailed proof is there. If you want to take a look at it. But as I said, that in this class we will not prove this particular theorem. So I'll just, as I said, give you the initial notation version of this particular relation. So in initial notation, in initial notation, you'll get that Wi is equal to minus half of epsilon I j k times W j k, and Wij is equal to minus epsilon I j k times W k. This is how you can write. So if you are given capital W, you can construct the small w. If you are given the small w, which is a vector, then you can construct the capital W. So here, let us just write it for, so suppose if I wanted W12, let's say because W11 will be 0, as I said, because all the diagonal elements of a skew symmetric tensor are 0. So there is no point in computing W11. In any case, that is also obvious, because if you put 1, 1, then the index is repeated, so it will be 0 anyway. So here, if I put 1, 2, right, then if I put 1, 2, then this can only be 3, right, because otherwise it will be 0. So this will be epsilon 1, 2, 3, W3, right. So and then epsilon 1, 2, 3 is 1, so this is equal to minus of W3. So your W12 will be equal to minus W3. And similarly, you can compute the other components also. So let me just write out. So suppose if you give me a vector W, which is W1, W2, W3, right? Then so using this particular relation, this Wij is equal to this, I can construct my capital W, which looks like 0. This is minus W3. So this is what I computed, right? The W12 was this one. Then this will be W2. This will be minus W1. Then this is 0. This is 0. Then again, this has to have the opposite sign. W3. Then this is minus W2. This is W1. Okay, so this is the skew symmetric tensor of which this is the axial vector. Okay, so you can actually carry out this computation and verify it for yourself that W times any vector U. So here you can verify that W times U is equal to small w cross. So this is a very useful relation actually. So for example, you are doing courses in rigid body dynamics, then this relation is used to define what is known as the angular velocity vector. Right? So this is a very useful relation. So here this W you will get in terms of an orthogonal tensor Q dot Q transpose. So that you will see in your rigid body dynamics class. And then the axial vector of Q dot Q transpose, which is a skew symmetric tensor, that is the angular velocity vector. See, suppose if the motion is planar, right? Suppose there is a disk that is rotating in its own plane, then uh, the angular velocity vector is fairly trivial because then that is just going to point so that is just going to point out of the plane. But suppose if you take a more complicated example, so suppose if you have a spinning top which is spinning like this, okay, so it is spinning about its own axis, and it is also spinning about one central line like this. So it goes like this, right? So that kind of motion to compute the angular velocity vector is not so trivial. So then, so this is the systematic way of finding out what the angular velocity vector is. Okay, so first you would have to compute Q dot Q transpose, where Q is an orthogonal tensor. Dot stands for the time derivative of that, and then from that you can take the axial vector of that and then get this. Okay, anyway, we will not get so much into the application. Another application would be in fluid mechanics, where this small omega would correspond to a vorticity vector. So this capital W would be a vorticity tensor, and then the axial vector of the vorticity tensor would correspond to a vorticity vector. So that you are familiar, right? Del cross V, correct? So that is the vorticity. So I'm saying there are lots and lots of applications of this particular relation. So we'll not go into all of them, but some 2 or 3 relations I've already pointed out. So here you can see that, let me just rewrite it again. So this is W is equal to W1, W2, W3. So so basically here you can see that this first element sits with a minus sign in the 2, 3 position. The W2 sits here, and then the W3 with a negative sign sits here. So given this vector, you can construct the skew symmetric tensor. And given the skew symmetric tensor, you can construct this. So what you do is you take the 2, 3 element, then reverse the sign, that will be the first element of this vector. You take the 1, 3 element, then that will be the second element. And if you take the 1, 2 element, then again reverse the sign of that one, and then you can get a vector. So you can go back and forth between the vector and the skew symmetric tensor, okay, quite easily. Another relation that I will write for the skew symmetric tensor and the axial vector. So that is another relation that I will mention here. So this W can also be written as norm of W times R cross Q minus Q cross R. Okay, so this Q and R are vectors such that W by norm W, Q, R form an orthonormal basis. Okay, so if I draw a picture, so suppose if I write this as W, then let us take the plane that is perpendicular to W, then this Q will be like this, right? So this is perpendicular to that. So W cross Q will be R. So you can imagine that R is something like this. Okay, so all of these are actually unit vectors. So let me just draw it. So this W is also W by norm W is a unit vector. The W itself need not be a unit vector, but W divided by norm W is a unit vector, and this Q and R are unit vectors. So these 3 vectors, they are orthonormal to each other. Now you can see that actually the Q and the R is not unique. because I can also draw a Q which is here and an R which is here. Correct? So the Q and the R actually are not unique. But see, we have already said that the W is unique. So what is happening is that although the individual vectors, here there should have been a tensor product. Yeah. So although the individual vectors R and Q, they are not unique, but this combination is unique. So some cancellation is happening of the non-unique part, and then finally you get a unique object. So here, one thing you can try and show is that use this particular relation and try to show that WU is equal to W cross. Okay, so try to show this using whatever, whether if you want to use initial notation or directly just use this particular relation and the definition of a diagonal product. If you try to show that, then that would be a nice exercise for you. Fine. So I think I'm not going to go too much into the properties of the skew symmetric tensor. Whatever I have defined and whatever properties I have stated, I think those will be enough for the moment. So we'll move on to the next set of tensors, which is orthogonal tensors. So let us look at orthogonal. So all these tensors play a role in actual applications. Okay? So you have to be very familiar with all the properties. So many times in rigid body dynamics, for example, the orthogonal tensor is going to play a very, very crucial role. So orthogonal tensor. So as I said, I will denote this set by OR, following the notation of Curtin, as I have said last time. So this is and the typical element of orthogonal we will denote by Q. Okay, so just like a typical element of the skew symmetric tensors we denoted by W, in the same way a typical element of orthogonal tensors either Q or R also. Many times R stands for rotation. So either Q or R. So that is how typically we will use these two symbols for denoting an orthogonal tensor. So Q, so let me define it. SOT, second order tensor Q, is said to be orthogonal. Is said to be orthogonal if Q transpose Q is equal to Q transpose is equal to I. So this is the definition. This is how we define orthogonal tensor. So from this definition, you can easily see that Q inverse, right, is equal to Q transpose. Right? When the inverse is equal to the transpose, right? So typically, if you write Q inverse Q, that is identity, right? So here basically your Q inverse is equal to Q transpose. So when the inverse is equal to the transpose, that is when we call it as a orthogonal tensor. Fine. So let us look at some of the properties of an orthogonal tensor. So we have the following properties. So we have QU comma QV is equal to U comma V, and we have QU is equal to U. This is for all UV, and this is for all U. This is for all U belonging to V, and QU minus QV norm is equal to U minus V for all UV belonging to. Okay. So actually all these properties they are equivalent in the sense that suppose let me just write as 1, 2, 3. So basically, 1 implies 2, 2 implies 3, 3 implies 1. So all these properties are actually completely equivalent to each other. So I'm not going to prove all the properties, but I will probably show the physical interpretation, which is much more important in this particular case. So if you understand the physical interpretation of these results, that is something very important here. So here, So suppose if I take two vectors, right? This is u and then this is v. So what it does, so suppose now you rotate this QU will rotate that particular vector basically. So you can see that it keeps the magnitude the same. It simply rotates that particular vector. Okay, and the same way it will rotate this V also. So here I will just draw that. So this V will be rotated version of that. So this will be QV. And suppose if the angle of this is theta, then the angle is preserved. So that is what here. So not only is the magnitude preserved, but the angle between those two vectors is also preserved. So here, of course, just for simplicity, I am drawing that Q is rotating them in the plane, but that of course is not necessary. It can rotate it even out of the plane, but just it is very difficult to depict something when it is being rotated outside the plane. So I am just showing it as an example. I am just showing vectors that are being rotated in the one plane, but that need not be always the case. So here you can see that this magnitude is the same, this magnitude is the same, and then the inner point. And then similarly, this QU minus QV, that is equal to U minus V. Yeah. So as I said, I will not prove the entire result. So this is the physical interpretation you should understand. So quite naturally, this Q plays a very big role in rigid body motion. Right? So that may, so see in a rigid body motion, what is happening? Right? So suppose if you take this and it is moving rigid, right? So it is a combination of a translation, right? So this is moving in all the three directions. So this is a translation, and also it is a rotation. Yeah, sorry. So the translation is it can move in this way, and also a rotation. So that means just you can see this that it's a any rigid motion is a combination, right, of translation and a rotation. So in order to, so the translation is very straightforward. You just add a constant vector, right, to the original position, then that will result in a translation. For a rotation, you have to multiply. So suppose if the position vector, if you multiply it by Q, which is an orthogonal matrix, then now this goes to a rotated position, right? And so in rigid body motion especially, this Q will play a very big role. And this Q will be typically time dependent, correct? So that means so it will not be a function of the position when you are studying rigid body dynamics, but it will be a function of time. So you see this, right? It is rotating as a function of time. So as I said, that this also has a lot of applications. So you should understand these properties quite thoroughly here. So here, let us try to show this. So as I said, some of these properties I will try to prove. So QU comma QV, if I use the definition of the transpose now, so this can be written as Q transpose Q times U comma V. Okay? And Q transpose Q is identity. So this is I of U comma V, and then this is equal to. So this is the first property here. So then if you choose U or V equal to U in this particular thing. So choose, so this is the proof for the first one. So the proof for the second one. So that means now if I want to go from 1 to 2, then choose V to be U. Then I will get that QU comma QU is equal to U comma U, and then so this implies that norm of QU is equal to norm of U, because that is simply the square root. The norm, if you recall, is simply the square root of that, and it's a positive quantity, so hence we are taking the square root of that, and so that the positive square root, and then you'll get that the norm is the same. And then from 2 to 3, so 3, just replace u by u minus v. So we are allowed to do that because u is arbitrary. So if I just replace u by u minus v, I will get this particular property. And if I want to go from 3 to 2, then simply set b equal to 0, correct? Because again, u and v are arbitrary, so you can go back to this one here. Some of these properties may be difficult. So, for example, to show that 2 implies 1 may not be so trivial. So, as I said, that I have not proved all of them, but again, all the proofs are there in the book in case you want to take a look at all the proofs. But I think what is important here is this kind of a physical interpretation. That basically, if you take a vector and if you multiply it by q, then you get a rotated version of that vector. So basically, the magnitude of that vector remains unchanged when you multiply it by q. Okay, and the second property is that if you take two vectors, right, they are simply rotated. And then, so the angle between those two, so not only is the magnitude of the two vectors preserved, but the angle between them is also preserved. So that actually property is obvious from this one here. Fine. If so here, let me just write this. So Q transpose Q is identity, right? Now, if you take the determinant of this, so then you'll get that determinant of Q transpose times determinant of Q is equal to 1. This is from the properties of the determinant. And then we have seen that the determinant of Q transpose is equal to determinant of Q. So determinant of Q square is equal to 1. So this implies that determinant of Q is equal to plus minus 1. Okay? So if the determinant is plus 1, then we call it as a proper orthogonal tensor or a rotation. So let me just write it here. So if determinant of Q equal to plus 1, then we call it as a proper orthogonal tensor. Proper orthogonal tensor or rotation. And if determinant of Q is equal to minus 1, then it is called improper orthogonal tensor. Improper orthogonal. So actually, typically in your rigid body dynamics, this will play a role because see so suppose you imagine that there is a set of axes that is embedded in your rigid body, and then as your rigid body turns like this, right, the orientation of the three axes that are embedded in your rigid body, that orientation remains the same, right? So what I mean is by orientation is that a right-handed coordinate system does not go to a left-handed, right? So if it's a right-handed orthogonal system which is embedded in the rigid body, as the rigid body moves, right, the orientation of that remains the same. That means your determinant of Q will be plus 1 in that particular case. So if you have a reflection, so for example, your y-axis flips, okay, to the minus y-axis, then that would result in an improper orthogonal tensor here, right? So as I said, that typically the rotation or the proper orthogonal tensor will play a role here. I think we will stop here. I think I have covered most of the properties. Okay, so we'll continue with this discussion the next time.